Hello, welcome to this lecture module on optics. In the last lecture, we discussed about reflection by spherical mirrors, and in particular we discussed formation of images by a spherical mirror. We also derived the mirror equation, which tells us precisely the position of the image when the position of the object is given. So, today we will move on, and today we will discuss refraction of light. To begin with, we will first discuss refraction at a plane interface, refraction of light. Refraction of light from a transparent medium, a transparent medium. It has been historically known for a long time that when light is incident on a transparent medium such as glass or surface of water, then a part of the beam is reflected back and a part of the beam is transmitted into the medium. Light incident on a reflecting surface, here it is a transparent dielectric, transparent medium. A part of the light is reflected back. We know that this satisfies the law of reflection, that the incident angle is equal to the emergent angle, and a part of the beam is refracted or transmitted into the medium. It was also known, it was also observed that the angle of refraction was not equal to the angle of incidence, while the angle of emergence here, that is the reflected angle, the angle subtended by the reflected beam was equal to the angle of incidence. The refracted angle here, that is the angle subtended by the refracted beam or the transmitted beam into the medium, was not equal to the angle of incidence. This was historically known for a long time. So, this is partial reflection and partial transmission of a light beam. A light beam incident, a part of it is reflected and a part of it is transmitted. So, this is called partial reflection. Now, if we consider an air water interface in particular, because water air interface is very commonly encountered in day to day life, that a light beam incident on a water surface, a part of it is reflected back and a part of it is transmitted into the medium. As long as in the year 140 AD, the Greek physicist Ptolemy had tabulated the angle of incidence and the angle of refraction. For different angles of incidence I1, I2, I3 etc., he had measured the angle of refraction and tabulated and given as a table. If this is the angle of incidence, then this will be the angle of refraction. But he did not know any further about the relation between them. However, in 1621 W. Snell formulated the following, that is, he observed, based on experimental observations, he found that sin I by sin R is a constant. For a given medium, for refraction at an interface, the angle of incidence, sine of the angle of incidence by sine of the angle of refraction was a constant. This is subsequently known as the Snell's law. So, the Snell's law. So, the Snell's law is now given by sin I by sin R is equal to n21, a constant. When we have an interface between a medium 1 and medium 2 of refractive index n1 and n2, then if I is the angle of incidence and R is the angle of refraction, then sin I by sin R is equal to n21, where n21 is called the refractive index of the second medium with respect to the refractive index of the first medium. That is, n21 is equal to n2 by n1. The first and second that we denote all subsequent discussions is the angle of incident, where the ray is incident, we call that as medium number 1, and there could be 2, 3, 4 and so on. So, the refractive index of the second medium with respect to the refractive index of the first medium. So, n21 is equal to n2 by n1. Note that n21 is greater than 1 if n2 is greater than n1. If n2 is greater than n1, n21 is greater than 1, and if n2 is less than n1, n21 is less than 1. This has some important applications, we will see this. The medium with higher refractive index, higher of the two, is called the denser medium, and the medium with lower refractive index is called the rarer medium. This denser medium density has nothing to do with the mass density, which is density is equal to mass by volume. So, this has nothing to do with that. This is denser here refers to a higher refractive index of the medium, and rarer refers to a lower refractive index. It is a relative term, relatively lower refractive index. It is not any absolute value, it is just relative to the other, one relative to the other, denser relative to the first medium here. So, rarer medium is a medium with refractive index lower than the second medium or the other medium. Now, let us see in particular refraction when light is entering from a rarer medium to a denser medium, and when it is entering from a denser medium to a rarer medium. So, note that angle of incidence I, angle of refraction here. I have considered air glass interface just as an example. Air is refractive index 1, glass is 1.5. So, this is rarer to denser, light entering from the rarer medium to the denser medium into the denser medium. So, sin I by sin r is equal to n21. Now, n21 is greater than 1 because n2 by n1 which is greater than 1. That implies sin r is less than sin I, which implies r is less than I. In other words, the ray bends towards the normal. So, this is the normal here, normal to the interface. So, this is the interface between the two media. So, this is glass, this is air, this is called the interface, and this line here is the normal to the interface, and the angle with the normal to the interface is the angle of refraction here, and the angle of refraction r is less than I in this case. When light enters from rarer to denser, light bends towards the normal, and when it is the reverse, that is when it enters from a denser medium to a rarer medium. So, for example, glass here and air here, this is the interface, then sin I by sin r is equal to n21, that is 1 by 1.5, which is less than 1, which implies sin r is greater than sin I and r is greater than I. In other words, the ray bends away from the normal. So, the ray here, the transmitted ray or the refracted ray bends away from the normal, which means bends away from its original direction. The dotted line here is the original direction. So, it bends away from the normal, whereas here the original direction is here, light bends towards the normal. The ray here we are referring to the refracted ray. Let us take now refraction through a glass slab, that is, now we will encounter two interfaces. Earlier we had discussed refraction at a single interface. So, now we are discussing refraction at a two interfaces, that is what happens. If we consider a glass slab here, a rectangular glass slab, then it has one interface here and the second interface here. At the first interface it is between air and glass, at the second interface it is glass to air. So, consider incidence of a ray here making an angle theta 1, then at the first interface the ray bends towards the normal, and therefore, theta 2 here, the refracted angle is theta 2. I have now used the notation theta when there are more than one interfaces or several interfaces, it is convenient to use theta 1, theta 2, theta 3 and so on rather than I and R, because there will be more R's and the same R would become I for the next interface and so on. Therefore, it is convenient to use theta 1, theta 2, theta 3 and so on. So, I have used theta 1 here. So, theta 1 and theta 2 is the angle of refraction. Earlier this was I and R, but now we have a second interface where this ray, that is the refracted ray at the second interface, subtends an angle theta 2, which is the angle of incidence now as far as this interface is concerned, and then theta 3 is the angle of refraction at the second interface. Now, applying the Snell's law at interface 1 and 2, at interface 1 here and interface 2, interface between two media, sin theta 1 by sin theta 2, that is the first one, is n glass by n air, that is n 2 by n 1. So, we have noted with the subscript n glass. So, n 1 is n air and n 2 is n glass, T is the thickness of the glass slab, L is the lateral shift. We will talk about L in a minute. So, sin theta 1 by sin theta 2 is equal to n glass by n air, and at the second interface theta 2 is now the angle of incidence. Therefore, sin theta 2 by sin theta 3 is equal to n air by n glass, that is n 2 now there is the third medium here, that is air, and therefore, n air by n glass. So, this simply gives you sin theta 1 is equal to sin theta 2. So, you can multiply the two equations and you see that sin theta 2 cancels, n glass cancels here, n air by n air is 1, and therefore, sin theta 1 is equal to sin theta 3, or theta 1 is equal to theta 3. What it means is, when the ray passes through the glass block, the ray which is coming out makes the same angle theta 1, which is equal to theta 3 here, which is equal to theta 1, which means as far as the direction is concerned, direction of the transmitted ray is concerned, there is no deviation. There is no deviation. However, there is a lateral shift, as you can see here, there is a lateral shift. So, no deviation, but a lateral shift of the ray, and this lateral shift depends on the thickness of the glass block, as we will see later. Now, I extend it further. So, we have now considered two interface, but suppose I have now several interfaces. So, we look at refraction through a multi-layered structure. Now, there are 4 layers, 1, 2, 3, 4, and of course, outside here air and outside here air. So, this is a stack comprising of 4 layers of different refractive indices. They are N2, N3, N4, N5 are different. So, this is a stack comprising of 4 layers, and therefore, there are 6 refractive indices, one from outside here and one here. Now, if we apply the Snell's law has to be applied at each interface depending on whether it is going from rarer to denser or denser to rarer, the ray will bend away or towards the normal. So, we can see here, for example, the ray here is bending away from the normal and again away from the normal. So, I have just taken some refractive indices, but we have not given any values here. So, if we apply the Snell's law at each interface, so the first interface theta 1 sin theta 1 by sin theta 2 is equal to n 2 by n 1, or we can cross multiply this, n 1 sin theta 1 is equal to n 2 sin theta 2. This is a more convenient form of Snell's law, n 1 sin theta 1 is equal to n 2 sin theta 2. If we apply to the second interface here, then it gives us n 2 sin theta 2, n 2 sin theta 2 is equal to n 3 sin theta 3, where theta 1, theta 2, the angles are indicated here. Theta 2 is the angle of refraction here, which becomes the angle of incidence when the second interface is considered. Theta 3 is the angle of refraction here, which becomes the angle of incidence for this interface, and so on. So, we have n 3 sin theta 3 is equal to n 4 sin theta 4, n 5 sin theta 5 is equal to, for the last medium theta 5 here is the angle of refraction, which becomes the angle of incidence here for this interface, and theta 6 here is the final angle of refraction. If these are all equal, it simply means n 1 sin theta 1 is equal to n 6 sin theta 6. If the first and the last medium are the same, in this case for example air, this was a stack of 4 layers, on both sides there is air, a ray of light was incident here and the ray is emerging from here. If the first and last medium are the same, it may not be same, it could be water. In another problem this could be water for example, but if they are the same, then theta 1 is equal to theta 6, which implies there is no deviation. That is, the final emergence angle theta 6 does not depend on the thickness and refractive index of the layers. Then what is the need? This is quite interesting to see that the angle of deviation, there is no deviation which is independent of the refractive index and thickness of the layers. Then what is the need to use such a multi-layered structure? There are large number of applications of multi-layered structures in optics. To understand this, ray optics will not be able to help us to understand and design these applications. We will have to go to wave optics. However, let us see something. So, we will come back to that a little later, and here we summarize therefore the laws of refraction. The laws of 1 and 2, the incident ray, the reflected ray and the transmitted ray or the refracted ray lie in a plane perpendicular to the interface. So, we can see here this is the incident ray, there is a reflected ray and there is a refracted ray, refracted or transmitted, because the energy is partially transmitted into the medium and partially reflected from here, and therefore, all of them lie in one plane perpendicular to the interface. Second is the Snell's law, which is sin theta I by sin theta r is equal to n 2 1 or equal to n 2 by n 1, which is more conveniently written as n 1 sin theta 1 is equal to n 2 sin theta 2. Theta 1 or theta 2 could be the angle of incidence. Now, we will discuss some natural consequences of refraction of light. So, some natural consequences of refraction of light. The first one that I have shown here is apparent depth. It is illustrated here. If we have a beaker of water or a container which has water, and if there is a coin at the bottom, I have taken a point P, maybe a point source here at the bottom, then it appears as if the depth where the point source is present is smaller compared to the actual depth. That is illustrated here. Why this is happening? So, you are observing from here, try to show I, and here is a point P, it could be a point source. So, therefore, light is emitted, it could be an object. We know that when we discuss the image of an object, then also we consider rays coming from a point on the object, and this could be a point source as well. So, point source, rays which come out from here are refracted at the interface. This for example is water and this is air. So, it bends away from the normal at each of these interfaces. We can mark the interfaces here. So, this is the interface, and if you draw the normal here, then light bends away from the normal, because refractive index here is smaller than refractive index here, and it bends in this direction. Therefore, it is a diverging beam. So, what you have here is a diverging beam, but all of them, if you extrapolate here, then they appear to come from a point P dash, from a point P dash, which is different from the actual point P. In other words, if we look from here, it appears as if the apparent depth. So, the point P dash, the depth of the point P dash, that is from the surface to the point P dash here is d dash. I have denoted it by d dash. The actual depth, of course, the point P is at the bottom of the container. The actual depth is d, and d dash is the apparent depth. D is the actual depth and d dash is the apparent depth. So, the apparent depth in this case is smaller compared to the actual depth. We can quantitatively determine how much it is smaller. So, let us just continue here and see this. Now, the equivalent problem I have shown here, the point P was here, a ray of light was at an angle I here, it is angle of incidence at this interface, comes out here with an angle of refraction r, an angle of refraction r, and the ray appears, if I extrapolate it here, that is if you were observing from here, the ray appears to come from the point P dash, and this angle here is r, because the angle of refraction here is r, and therefore, this angle is r. Angle of incidence I is here, and this angle is also I, because these are two parallel lines. So, this is a ray which is normally incident, which transmits through the medium. Of course, it is also partial transmission, everywhere it is partial transmission. So, d dash is the apparent depth, d is the actual depth. Now, for small angles I, these are actually small angles, because we are looking from here. So, I can show the I which is here. So, the I is here actually. So, this is the I which is observing the point P. Now, therefore, the rays which enter I are those which make very small angles. The ray which would come here would enter the I. A ray which is coming here is any ray which is making a larger angle does not enter I. So, all the rays which enter your I here is the ones which make very small angle. Therefore, the approximation is very much valid for small angle I and r. If I is small, r is also small, although r is a little larger than I, but it is still quite small. Therefore, we can write sin I nearly equal to tan I. For small angles theta, sin theta is nearly equal to theta is nearly equal to tan theta. So, sin theta, sin I is equal to tan I from this triangle here, triangle P Q R, tan I is Q R here divided by P Q, this length P Q. And similarly, sin r nearly equal to tan r is equal to Q r divided by P dash Q, this length, and therefore, sin I by sin r is equal to n 2 by n 1 by Snell's law. Sin I by sin r, if we divide one by the other, it is P dash Q by P Q, which is nothing but d dash by d. So, apparent depth divided by actual depth is equal to n 2 by n 1. N 2 is always the second medium, n 1 is the first medium by notation. Usually, n 1 is air, n 2 is air, that is from where we observe is air, as in our problem. Our problem, this is the liquid where the point was at the bottom of the container, and here it is air. Apparent depth is equal to actual, n 2 is equal to 1. Therefore, actual depth. So, if we take apparent depth, actual depth comes here, actual depth divided by refractive index of the medium. The apparent depth is equal to actual depth, n 2 is 1 divided by n 1, which is the refractive index of the medium. So, apparent depth is equal to actual depth divided by refractive index of the medium. So, if we consider glass or water, then we see that the apparent depth is smaller compared to the actual depth. So, this everyone can observe this in practice. We will take up some numerical to illustrate this point further. As a second example, we look at the inclination of the setting sun, apparent inclination or apparent position of the setting sun. So, the diagram here is not to scale, it is just a schematic, because what I have shown is the earth has an atmosphere around it up to few hundred kilometers. Earth has an atmosphere, this is of course several thousand kilometers. Therefore, this diagram is not to scale. So, earth surrounded by an atmosphere, and beyond that of course, it is free space, and the stars and sun are in free space which are far away from the earth. So, this distance is of course much larger compared to the thickness here or the width here of the atmosphere. So, it is not to scale, but just a schematic illustration. So, what is being illustrated is the following: there is an observer here on the surface of the earth. The size of the observer is of course negligible compared to the dimension, again not to scale. So, the observer here looks at the sun. If this is the horizon, then the observer is looking at the sun, his apparent position of the sun is here, he is seeing the sun which is above the horizon, but the actual fact is that the sun is below the horizon, because when the sun is here, I consider a typical ray, one ray, just to illustrate the ray which is coming from the sun. There are of course large number of rays, a bunch of rays which are coming, but a ray which is coming like this, when it enters the atmosphere, free space or vacuum has refractive index n is equal to 1, exactly 1.0, and atmosphere here which has air and other gases has refractive index slightly more than 1, maybe 1.00 something, but it is slightly more than 1, and therefore, the ray is entering from a rarer medium to a denser medium, and it continuously bends towards the normal. We can stratify this. For example, we can see that this is when it is entering. So, this is the atmosphere. So, the ray is entering like this, the ray is entering. Here there is a higher refractive index. Therefore, if I stratify this, that is, if I consider this into a large number of layers, then the ray which is incident here bends towards the normal. So, it bends towards the normal, it bends towards the normal, it bends towards the normal. So, it is slowly, because why slowly? Because the refractive index here is 1 and maybe here it is 1.0078 or something like that, but it is slightly larger, and therefore, the ray is continuously bending towards the normal, and therefore, we see that however, the observer who is here, when it reaches the observer, then the ray is entering his eye like this. So, it appears to him as if the ray is coming from some point here. So, if this was the position of the actual sun, then the sun appears to him as if it is coming from a point which is here, whereas the horizon is here. So, this is the horizon. So, that is the diagram. So, let me put the pre-drawn neat diagram here. So, the ray we can see here starts bending and continuously towards the observer, and the observer finds it as if it is above the horizon. So, this is what is known as inclination, the apparent inclination of the setting sun. This is an illustration which shows that although the refractive index is very small, because the length of the atmosphere is of the order of 100 kilometers or 200 kilometers, then it starts over that period, it bends significantly, and there is a significant difference between the actual position of the sun and the apparent position of the sun. So, we have these two natural examples which I have illustrated. So, we will take up some numericals to illustrate refraction of light, and let me take up some examples. Okay. So, we come back and with these examples what we have we have got a better appreciation of the refraction of light, and there are numerous problems which are possible, particularly the multilayers are very important, and let us take some examples now to illustrate what we have studied. So, here a narrow beam of light travels from medium 1 through 3 layers of different transparent media into medium 5 as shown in the figure. So, see the figure, a narrow beam of light travels from medium 1 here through medium 2, medium 3, medium 4 into medium 5 as shown in the figure. Rank the media in ascending order of their refractive indices. So, we have to find out which is the medium with the least refractive index to which is the maximum one, and therefore, we have to rank them or list them in ascending order from the lowest to the highest refractive index. So, the data, the figure shows angles here 45 degree, 30 degree, 40 degree, 50 degree and 35 degree here. So, how do we go about this? So, we use the Snell's law. We will use the Snell's law in the form that n 1 sin theta 1 is equal to n 2 sin theta 2 is equal to n 3 sin theta 3, etc., or n I into sin theta I is a constant for any given medium. So, we apply it to this and find out which one would be the lowest refractive index. So, here, so use Snell's law, n I sin theta I is equal to constant. So, a medium which has the largest angle here, which means sin theta will be largest, n I sin theta I is constant. Therefore, when the angle here, that is theta I, this becomes theta I here, this is theta r, but theta I here. So, when the angle is the largest, the refractive index must be the smallest, because sin theta I increases with theta I, and therefore, medium 4 must be having the smallest refractive index. So, medium 4, the smallest one is medium 4, the largest angle. So, medium 4 will have the smallest refractive index. So, let me rank it in that order, in the ascending order of refractive index. So, this will be 1, medium 4, and then the next angle that we see is 45 degree here, the largest, next largest angle is 45. Therefore, medium 1 will have the next higher refractive index. So, 2, medium 1, medium 1. Then we have 40 and therefore, 3, this is medium 3. So, medium 3 here, and then after 40 we have 35. So, 4th will be medium 5, and finally, the smallest angle that we have here is for medium 2, and therefore, this will have the largest refractive index. So, 5, medium 2. So, we have now ranked the various media here in ascending order of refractive index. Medium 2, where it makes the smallest angle, will have the largest refractive index, and medium 4, where it makes the largest angle here. This is the rarest medium among all of them. You can see that it is the rarest medium, that is why it goes well above the well beyond the normal, bending away from the normal, making a large angle 50 degree here. So, medium 4, 1, 3, 5, 2. So, as I mentioned that when we have several media, then it is easier for us to write the Snell's law in the form of sin theta I, n I sin theta I is a constant for every one of the media. So, this is like a quiz question, very quickly we can identify without doing any mathematics, just looking at the angle we can identify which are the media that have largest refractive index. Let me take another example here. So, let us go to the next example. A glass beaker of height 10 centimeter contains water of refractive index 1.33 up to 4 centimeter height from the bottom, and then a transparent oil n equal to 1.31 above water up to the top edge of the beaker. So, this here I have tried to draw the diagram. So, there is a glass beaker here, the first of total height 10 centimeter, and the first 4 centimeter is filled with water, n is equal to 1.33, and the next 6 centimeter is filled with that transparent oil of refractive index n is equal to 1.31. So, what when viewed from above, that from the top, when viewed from the top, what would be the apparent depth of a small coin located at the bottom of the beaker? There is a small coin placed here at the bottom of the beaker. What would be the apparent depth when viewed from above? So, this is actual depth is 10 centimeter, but will it appear as 10 centimeter deep, or will the apparent depth is smaller or larger than the actual depth? That is the question. So, to determine the apparent depth of the bottom of the beaker, actually a small coin is placed, or it could be a point source, it could be a point P at the bottom of the beaker, but basically to estimate the apparent depth of the beaker. So, let us comprehend this problem a little bit more carefully. So, here is the beaker, let me draw that again. So, the beaker, and there is water up to a certain level. So, 4 centimeters of water. So, this is 4 centimeter and this is 6 centimeter, 6 centimeter. So, this is of refractive index 1.31, this is 1.33, slightly different refractive indices, and viewed from above, which means you are viewing from the top here. So, viewing from here. So, that means the eye is here, I am showing eye, a little bigger eye just for convenience. The point to see is when you view this, a bunch of rays enter the eye. There is a small cone. So, a cone over which rays enter the eye. So, rays enter over a small cone coming from the bottom. If I have at the bottom a point P, or there is a point P here, a point source P, then a bunch of rays which come out will enter the eye over a small cone. This angle here is very small, the angle of the cone is very small. However, this, as we will see, will lead to an apparent depth, and we are asked to determine the apparent depth of the coin in this mixture of in the liquid in the beaker containing two different liquids. So, here I have drawn a more neater figure to illustrate the problem more carefully. So, here is the solution. So, the first medium of refractive index n1, height h1. So, I have not put any numbers, we are handling it in general analytically, and second medium is of refractive index n2 and of height h2, and the third medium which is here outside, which is air in this case, let me call it as n3, and here is the eye is here. So, we are viewing from here, the eye is here, but I have right now taken. So, in the last diagram that I had made, I showed that in practice this angle is very small when you are viewing from the top, but it is not necessary that I should be viewing from the top, I could be viewing from an angle. So, even then a small cone of rays would pass through this. So, I may be watching from here. So, my eye could be here. So, this is viewing from above, but this is viewing at an angle. So, this angle I may be watching at an angle of 40 degrees for example. So, both cases keeping both cases in mind. So, here I have tried to analyze this problem. So, here it is from the point P, the point source here, ray which is coming here is incident at an angle theta 1. So, the refracted angle in medium 2 is theta 2 and the refracted angle in medium 3 is theta 3. So, see the diagram. So, if you are watching from here, so if the eye is here, so you may not be able to see, let me draw an eye there. So, here is the eye. Then, so I is watching this point, observing this point which is coming at an angle theta 3. From the geometry what we can see is, if this angle is theta 3, this angle is theta 3, I have marked this distance as x 3 and therefore, from the geometry we can see that h 1, h 2 are the thickness of this water column here and h dash, h here, h is the apparent position of the point object P. There is a point object here, but I sees it as if the point object is located here. In other words, h is the apparent depth. In this problem, h is the apparent depth. So, we have to determine what is h, the apparent depth. The actual depth is of course h 1 plus h 2, the total height from surface to the bottom, h 1 plus h 2, but the apparent depth is h. So, looking at the geometry, x 3 by h is tan theta 3 or h is equal to x 3 by tan theta 3. Now, from the geometry we can also see x 3 here is equal to x 1 plus x 2, because this is parallel, it is parallel to the normal here, this is also a normal, and therefore, x 2 plus x 1 is x 3 and therefore, h is equal to x 1 plus x 2 by tan 3. However, x 1 here is equal to, this height is h 1 and therefore, x 1 by h 1 is equal to tan theta 1, x 1 by h 1 is equal to tan theta 1. Therefore, x 1 is equal to h 1 tan theta 1 and x 2 similarly, this is h 2 and this is theta 2 and therefore, x 2 is equal to h 2 tan theta 2 and therefore, h 1 is equal, therefore, h is equal to x 1 by tan theta 3 plus x 2 by tan theta 3, that is h 1 into tan theta 1 by tan theta 3 plus h 2 into tan theta 2 by tan theta 3. Note that we have not made any approximation here. There is no approximation involved and therefore, this is valid for any angle theta which is at which the observer is looking at the coin. And therefore, if we know that the observer is looking at an angle theta 3, I can calculate theta 2 by using the Snell's law, because the refractive index of the media are given n 1 and n 2 and n 3 and therefore, I can calculate theta 2. If I know, I can calculate theta 1 and therefore, I know tan theta 1, tan theta 2 and tan theta 3 and therefore, h, the apparent height h is equal to apparent depth h is equal to h 1 into tan theta 1. I can exactly calculate this. For any theta 3, theta 1 and theta 2 can be determined using Snell's law. However, in this problem it is said viewing from above. Viewing from above means we are viewing right from above, which means as I indicated in the problem, a small cone here. So, we are looking at from above, which means a small cone of angles which we are considering, which enters the eye, and therefore, viewing from above implies the angles theta 3, theta 2, theta 1 are all small angles and therefore, tan theta 3 is nearly equal to sin theta 3, tan theta 2 nearly equal to sin theta 2 and tan theta 1 nearly equal to sin theta 1. This approximation is very much valid for all small angles. And if we apply that and substitute here that instead of tan theta 1, if we substitute sin theta 1 by sin theta 3, sin theta 2 by sin theta 3, then we will get h is equal to h 1 by n 1. So, we can simply substitute that and see. So, h is equal to h 1 into tan theta 1, which is approximated by sin theta 1, sin theta 1 by sin theta 3 plus h 2 into sin theta 2 by sin theta 3, sin theta 3. So, we know that n 1 sin theta 1 is equal to n 2 sin theta 2 is equal to n 3 sin theta 3 and therefore, sin theta 1 by sin theta 3, sin theta 1 by sin theta 3 is n 3 by n 2. Therefore, this expression here is h 1 into n 3 by n 1 and plus h 2 into sin theta 2 by sin theta 3. So, this comes here and so this is n 3 by n 2. So, h is equal to h 1 into n 3 by n 1 and because our surface here is air, we are looking through the liquid medium here. Therefore, it is understood that it is air here. Therefore, n 3 is equal to 1. With the n 3 is equal to 1, we have h is equal to h 1 by n 1 plus h 2 by n 2. So, that is what is written here, h is equal to h 1 by n 1 plus h 2 by n 2 with n 3 is equal to air. And therefore, we are asked to find out the depth. So, what is the answer? Therefore, answer the apparent depth h is equal to h 1 by n 1 plus h 2 by n 2, h 1 is 4 centimeter and refractive index is 1.33 plus 6 centimeter divided by refractive index 1.31 and which comes out to be 7.59 centimeter. So, the apparent depth of the coin is 7.59 centimeters. There are several variations of the problem which is possible. So, n 1 can be maybe larger than n 2, n 2 may be larger than n 1 and so on, several combinations are possible. There is also an interesting extension. So, here it is. So, let me just discuss an interesting extension. A particular, so here is a point P, could be a point source P, which is observed by an observer here. So, the actual height that he would see or the point P is located at some depth here. So, some depth d. Now, we introduce a block. So, if someone introduces a glass block of certain thickness t and refractive index n. So, this was here. Now, a block is introduced, a glass slab is introduced of thickness t and refractive index n. So, where will the point P now appear to be or what is the shift? So, this is going to shift. So, it may be shifting here or it may be shifted here because of the introduction of this, because there is a refraction which is taking place and therefore, we are asked to find out, determine the shift in the. So, this is the object now, this point P is the object. So, I can also call this as O. So, this may be shifted to a point O dash, I am just showing it here O dash. So, determine the shift. So, shift is this. So, what is the shift? So, this shift I can call this as S or delta H or delta D, whatever S, the shift, determine the shift, determine the apparent shift. The object is of course there, but it is appearing. So, determine the apparent shift of the object, It just occurred to me. So, I had not drawn any pre-drawn any diagram. So, we can just determine the shift. So, let us take so this is D. Now, if I draw a line here, we can simply extend the earlier problem. So, let me draw afresh. So, the object is here O, we have introduced a glass block here of certain thickness. So, let us say this is T. This was the original position, and therefore, let me call this. So, this is, let this be L, let this distance be L, because I am interested only in determining the shift. So, shift O and O dash, O dash. So, let this be L, and so this is the shift to be determined, this is S to be determined. I can think of just extending the previous problem where we had apparent depth. So, L and L dash. So, if I call this as L dash, so this new position as L dash, please see earlier we had H actual height and H dash as the apparent depth. So, I am now calling it as L and L dash. This height does not matter because it remains the same, there is no change taking place, and therefore, if I determine L minus L dash, that will give me the shift. The shift is simply L minus L dash. So, to determine L dash, what we had done was earlier, if we remember that we had T of a thickness T of refractive index n1 and the remaining part here, that is L minus T. So, the total length is L. So, I can write this as L dash T by refractive index n plus, I am just extending the same result L minus T, that is this, and we know this refractive index is 1 here because this is air, this is air, this is air, a glass slab has been introduced, a glass slab of thickness T has been introduced. Therefore, L minus T divided by 1, refractive index is 1, and therefore, this is what we have, which means L, therefore, L minus L dash. So, I bring L dash here. So, there is a T also. So, T goes to the other side is equal to T into 1 minus 1 by n, T into 1 minus 1. I have simply applied the result, the earlier result which said that H, that apparent depth was equal to H 1 by n 1 plus H 2 by n 2. So, in this case H 1 is this thickness T by n, and the remaining length which is L minus T, I had called the total length as L. Therefore, L minus T is equal to which is of refractive index 1 because that is air, and therefore, L minus L dash is nothing but S. So, the shift S is equal to T, the thickness, into 1 minus 1 by n. It is very interesting indeed. See that it does not matter where you introduce the slab. The slab could be introduced here, the slab could be introduced here, anywhere the slab could be introduced. The shift simply depends on the thickness of the slab and the refractive index of the slab. So, it is just a variation of the other problem which I had discussed earlier. There are several possibilities, and I would suggest that you work out a number of problems to get a better feel of this subject. A second part which I would also recommend you to take it as an exercise is to determine the lateral shift. I had not worked it out here. So, we have a ray of light incident like this, it bends towards the normal if this refractive index n is greater than the refractive index here, and then it again bends away from the normal. If the media are the same, the angle that it subtends here theta is the same as the angle it subtends here, which means we said there is no deviation. T is the thickness of the glass slab and n is the refractive index of the medium. So, what we have got, we have already discussed this, that we have lateral shift. So, what we get is a lateral shift here. So, which I think I denoted as L. So, find an expression for L, find an expression for L. for the lateral shift. We can extend this problem by taking two slabs. So, like we had done for the apparent depth, for the lateral shift also, suppose you had two slabs one after another. So, this is of thickness T 1 and this is of thickness T 2 and refractive index N 1 and N 2, and outside of course, it is N 0 or air, you can say this is 1 and this is 1, which means again as we have already discussed, there is no deviation. However, the lateral shift, so let me show the lateral shift here. So, this is bending towards the normal, maybe it will bend a little bit away, but finally it will come out in such a way that it will be parallel to this. In other words, there will be no deviation, we have discussed this several times, only there will be a lateral shift L. Now, the lateral shift will depend on N 1 and T 1 and N 2 and T 2. So, determine the lateral shift. Follow a procedure which is almost similar to what I have outlined here and determine an expression to obtain an expression for the lateral shift. So, there can be several similar problems. Thank you.